Hi, Peter Dorman, and the topic today is economics and ecology. Far more than can be covered in a short introductory talk, but we'll try to hit some of the high points. One of the high points is the very concept of a commons, which is in many ways the entry point in discussing the relationship between economics and ecology. We'll consider the issue of natural resources, the different forms they take, and how economists look at them. The general question of pollution, of course, which is on people's minds when they think of ecology and economics. The interaction between ecological complexity and economic complexity, a difficult topic, but one worth at least bringing up. And finally, a few words about the issue of risk and precaution as a response to risk. So let's begin with the idea of a commons. Economics typically assumes that everything out there is owned by somebody, that it's property. And so economists look at how property is exchanged between people or used in order to make profits or for some other economic purpose. However, when you think about it, most of the world is not owned by anyone. Now that includes nature, for sure. So we're talking about the atmosphere, the oceans, biodiversity, ecological cycles. Most of what makes nature is not owned by anyone. On top of that, human culture is a commons. It's also not owned by anybody, and that includes things like language, culture, mathematics. Most branches of knowledge are shared in some general way and are not anybody's private property. If we want to drill down one level, we can ask what makes a commons, what's characteristic of it, and there's actually a lot of disagreement about that, and different people have different approaches to it. I would focus on three general characteristics which more or less seem to obtain whenever we have something like what we call a commons. The first, of course, is that it is unowned. That's by definition, if it's owned, it's not part of the commons. So the first point being it's unowned. The second is typically that it's difficult to own it. It's not suitable to be owned, either because it doesn't have clear boundaries or lines of demarcation where you can say, I own this part of it and you own that part of it. So the atmosphere, for instance, it's pretty difficult to set up fences in the atmosphere. On top of that, the issue of indispensability is important. Again, think of the atmosphere. It is indispensable for a number of ecological purposes and, of course, as a source of oxygen for us. Even if somebody could own it, you wouldn't want somebody to own it because they would have tremendous control over you by virtue of the fact that you are so dependent upon it. So the commons typically has those two features. And then finally, most commons are self-reproducing. Unlike physically produced objects, things that people create, where people need to create and recreate them, the items that are part of the commons typically reproduce themselves, and if people stand aside, for the most part, the commons will take care of itself. So if the major economic question for most of the owned world is how do we get people to produce it, the main question for the commons is how do we get people to not interfere with it? The modern discussion of the commons owes a lot to this guy, Garrett Hardin, who is a biologist and wrote an extremely influential article in the 1960s called The Tragedy of the Commons. It basically tells a story. His story goes like this. So there are several shepherds, and they share a pasture between them. The pasture is not owned by anybody, so it's freely accessible by any of the shepherds and their sheep. Now, each shepherd wants their sheep to be as well-fed and productive as possible, so they all have an incentive to send their sheep out to graze on the pasture. But the pasture can be overgrazed, and if it's overgrazed, it loses its ability to support sheep. And in the absence of any type of control, what will happen, according to Hardin, is that these shepherds will just send their sheep out, the sheep will eat up everything that grows, and the next thing you know, you have a wasteland that doesn't support any sheep at all. That's the tragedy of the commons. The tragedy is avoidable in only one of two ways, he says. Either you privatize the pasture, that is, you have an individual owner, or some group would own the pasture and then would be in a position of selling it to anybody who wanted to have their sheep accessing it, and that price would reduce the use of it and eliminate the tragedy. Or you would need to have government regulations that said you can only send your sheep out on such and such a day for so many hours or whatever it would take in order to preserve the pasture. So it's a very pessimistic story which only has a couple of ways out, a market or direct government control. However, along came Elinor Ostrom. Elinor Ostrom was a political scientist, but interestingly was the first woman to win a Nobel Prize in economics in 2009. She had published a book at the beginning of the 1990s called Governing the Commons, and it was a direct response to Garrett Hardin. She had a completely different view of things. She began with the initial premise that actually, if you look throughout history, human communities have governed commonses pretty well. If you're going to talk about shepherds and pastoreds, well, there are many pastoral societies around the world that used their common grazing areas as a commons, and they didn't all go extinct. They managed generation after generation to find some way to keep their economies going even while sharing the pasture. And theoretically, we understand how that could happen because there's a branch of game theory that discusses how people can evolve towards cooperation in what's called a repeated prisoner's dilemma. The prisoner's dilemma has been discussed previously, and we'll get back to it later, probably, in this lecture series. The main point here being that if you allow people to interact over and over again, it is quite possible for them to evolve cooperation with each other and develop a system of mutual collective government to resolve issues like the tragedy of the commons. Now, she went beyond these very general observations to actually try to figure out what are the ways in which communities have successfully managed to govern their commons, their common property resources, and persist over time. So her research program that she engaged in and then got others, students and colleagues to work on, was to scour history and the contemporary world for as many examples as they could find of successful management of the commons, and then to distill what they learned into a set of rules that could be followed. The fundamental premise of her work, which really is the basis for everything, is to distinguish between common property resources, i.e. a commons, and open access, which is what Garrett Hardin assumed in his story of the tragedy of the commons. That is, that the pasture is simply open and freely available to anyone who uses it. What Ostrom realized is that something could be a commons. It could be unowned by any entity, and it could have all the characteristics of a commons that we described, and yet there could still be a management system by a community that recognized its common interest in preserving the commons and its contributions to their livelihood. So understanding how to manage a commons means really how to set up restrictions on access or to manage access so that the commons can survive. One particular solution to the problem of commons, which has attracted a lot of interest, is the institutional form of a trust. Now, that's a modern concept. Most human societies have nothing like it, but increasingly in our world, we see trusts being turned to as instruments for managing common property resources. So here are some examples. A trust is any organization whose mission is to preserve the non-economic value of a common resource. We have land trusts. So a land trust takes some kind of responsibility for some amount of land. It could be just a small parcel or a larger piece of land. And its purpose is to preserve the larger value of that land, not just its economic value, but its ecological value or cultural value as well, through the generations. Similarly, we have trusts that engage in historic preservation, where the built environment, which might be of great cultural and historic value, some famous person's house or some historic district, might be preserved by a trust whose mission is to maintain its historic character over time. There's been a proposal to establish a trust in connection with dealing with climate change, where the atmosphere might be considered a common property resource held in trust for the people of the earth, and as such could accumulate assets which could, or income, which could be distributed to the people of the earth, who in some sense are its beneficiaries. And the trust could be a form of organization which would whose mission would be to preserve an atmosphere that did not overheat the planet. The idea of a trust is intriguing, but it does have the problem of, like any human institution does, of how do you guarantee that it's going to live up to its stated mission? Let's turn to resources. Broadly speaking, economists distinguish between renewable resources and non-renewable resources, so we'll take them up one at a time. A renewable resource is something which is reproduced naturally through some kind of biological or physical process, or a process that combines both together. So there are many examples of this. Fresh water is a renewable resource. Populations of animals that we rely on, anywhere from bees to animals that people hunt, to animals that are used in other ways, a renewable resource. Forests are renewable resources. Topsoil is a renewable resource. Many of the things that we get from nature take this form. And the question that economists have asked themselves historically is, how should these resources be harvested? How should we gather them? And specifically, how intensively should we harvest them? The problem is that we could, in theory, err on either side. If we harvest too much of them, if we take too much too quickly, we'll destroy the resource. We'll eliminate the stock that we rely on, and we'll get back to that in a moment. If we do it too slow, well, the problem here is that we're not taking advantage of an opportunity that's available to us. That may or may not be a problem, but if the resource is valuable, if it's something that we could really use productively, it might be unwise to harvest substantially less than we could. So the question is, what's the middle zone, the sweet spot, where you properly balance off the risk of doing too much and the risk of doing too little? There are many examples that we could look at. Biologists, for instance, are involved in setting up fishing quotas for fisheries, where on the one hand there is a lot of demand for fish. People want to fish and eat fish. On the other hand, the fish stocks have to be preserved for future generations. So it's very important to find the biologically reproducible level. Groundwater. In eastern Washington, we depend tremendously on the use of groundwater for irrigating crops. And it would be a tragedy if we pumped out too much water too quickly and destroyed the basis for agriculture in an entire region. On the other hand, you don't want to turn pumping down to zero, because aquifers are recharged and there is a renewable supply of groundwater which human beings could take advantage of. Broadly speaking, the analysis is summed up in this diagram. On the horizontal axis, we see the stock of a resource, where the resource is called R, and the stock is the total amount of that resource that's available. That could be the size of a fishery, like how many fish are in the ocean, or it could be how many trees are in the forest, or board feet of timber, or some other measurement, or how much flow of water per year we have in an aquifer, or something of this sort. So it's how much of the total resource there is. And then on the vertical axis, we have the change in the stock of the resource as a function of how big it is. That's the growth rate of the resource. So typically within a certain range, the resource will grow over time. Trees grow, animal populations grow. If the groundwater is below its maximum level, it will recharge in such a way that the volume of water under the ground will grow. So we would expect there to be some relationship between the growth of the stock and the stock. That's summed up in the thick line, the upside down U that you see in the diagram. At a very low level of the stock, it's not reproducible. It's just too small to reproduce itself, and it gets smaller and smaller every year until it disappears. And so that the critical point here is point A. Point A is the minimum viable stock. At point A, if you're below point A, the stock will disappear. Think, for instance, of an animal population. If it falls below a certain level, it will become extinct. Point A is the minimum size of the animal population at which it will not become extinct. And then there is another point, C, which is the maximum size the population could be at, or the size of the stock, if human beings had no interference at all. So again, if it's an animal population, the population will increase and increase and increase until it reaches such a size that at that size, there's no more tendency for the population to go up or down over the long run. And that means that delta R, or change in R, the change in the stock size, would be zero. If for any reason the population exceeded that, that would be exceeding the carrying capacity, and we would expect actually a reduction, a negative growth in the population until it returned to C. So if it was to the right of C, there would be a negative growth, and then that would cause the population to go back to C. A very interesting point for us is point B. Point B is the profit maximizing size of the population. And what do I mean by that? Well, the slope of the line at any time indicates the rate of change in how much you can harvest sustainably from the stock, that's delta R, that rate of change with respect to the size of the whole stock. In other words, it's a kind of rate of return to allowing the stock to grow on its own. And that rate of return could be compared, for instance, to the rate of return on money, or the interest rate, which is also a kind of slope. And what B represents is it's the size of the population at which the rate of return on keeping the stock in the ground, whatever the resource is equal to the rate of return on money. If we were to the left of B, if we were harvesting less, then the growth rate of leaving things in the ground, or leaving the population, not harvesting, would exceed the rate of growth on money, or the rate of return on money. In other words, the slope would be steeper, as it is to the left of B. And if we're to the right of B, the slope is flatter. In other words, money has a higher growth rate. So we're comparing the growth rate of money to the growth rate of the stock. Now, in just ordinary language, the way to think about that is that harvesting takes something that used to be a natural resource and turns it into money. If you're harvesting fish, if you're a fishing operation, you take fish from the ocean and you sell them and turn those fish into money. So when you're thinking about whether to fish or not, to harvest or not, the obvious question that comes up is, well, if I left the fish in the ocean and the fish reproduced, would there be let's say, a bigger supply of fish the next year? So the fish would grow, so to speak. We could invest in fish. But we could also fish the fish, sell them, and put the money in the bank and invest in money. And each of those two options gives us a certain rate of return. One is the rate of return of resource growth, which is given by nature. And the other is the rate of return on the interest rate, which is given by the human economy. So if you compare each different use of the resource, that gives you an idea of how much to harvest. So if it's the critical variables here are the natural resource growth rate, which is given by nature, and the interest rate, which is given by the human economy. And it's the comparison of those two that then determines what might be the profit maximizing level of resource use. And if you believe the market welfare model, it's also the socially optimal level of resource use. A side issue is the question of ecological services from renewable resources. So in addition to being harvestable for economic benefit, Many natural resources provide ecological values for us that are extremely important. So preserving water quality or biodiversity and so on. So then the question is, what determines what economists would say about how these resources should be exploited? And one approach would be an ecological approach, which is to say, well, we need a certain amount of these services. Let's just set up some rules that guarantees that we're going to get that. However, economists would tend to prefer a different approach, which is to put a price on the services, to say, how much is it worth? What would be people willing to pay for this or that ecological service? And then either pay people you could either subsidize people to provide those services, or you could have fees or fines if they failed to provide the service, implementing those prices, making it a market good, and using that approach to preserving ecological services. Most people who call themselves ecological economists are engaged in the enterprise of trying to put dollar values on ecological services. And if you read the journal Ecological Economics, probably the majority of the articles in that journal in any given issue will be about efforts to put monetary values on ecological services. One example of that, which has been much discussed in Europe and discussed a little bit in the United States, is paying farmers to preserve the ecological integrity of the landscape that they farm. Let's move to non-renewable resources. Non-renewable resources have a fixed supply in theory. Of course, it may not be entirely fixed, but in theory, it's perfectly fixed. So an example of that would be petroleum. There's a certain amount of petroleum under the earth. It's formed by a geological transformation of carbon stored in the Earth's crust or under the Earth's crust as a result of past terrestrial and marine life. And it's a very slow process. It takes millions upon millions of years to turn these carbon residues into fossil fuels. So from a human point of view, the supply of petroleum and coal and natural gas are essentially fixed. Any amount that we use today is less that's available tomorrow. So how much should we use? In some ways, it's similar to the question of renewable resources. So if we use too much, we use it up, there's none left, and we're sorry that we did this terrible thing. On the other hand, using none of it doesn't make a whole lot of sense, because there's potentially an immense human value that can be obtained from these. If we were suddenly to stop all mining for ores and all drilling of fossil fuels, it would be very difficult for us. We might want to phase a lot of this out, but moving to zero immediately is not much of an option. So we have to once again find the sweet spot. And economists have, in their cleverness, developed various so-called optimal depletion models, different ways of modeling the problem of how quickly to use up these resources. And there are certain characteristics to their solutions. One is that an economic model typically will call for using up the entire stock of those resources. So typically there's nothing left at the horizon of the model. And the defining characteristic of such an optimal use pattern would be that there would be no way that you could move some use from one time period to another. So use a little less in one period, a little more in another period. No way to do that that would make society better off in any way. These types of models depend on the market welfare assumptions, and then they produce various guidelines that economists often recommend that we follow when we use non-renewable resources. So what do they say? Well, they say that how quickly we use them up should depend, logically, on what alternatives we have to these non-renewable resources. In theory, if we use them, if there are good alternatives available now, we shouldn't worry so much and use them up more rapidly. But it may be the case that these alternatives need to be developed. in which case we should slow down and provide more opportunity for development of alternatives in the future. Another consideration is interest rates, just like with renewable resources. So the higher the rate of interest, the more pressure there is to extract a resource, convert it into money, and enjoy that high rate of return on money, rather than leaving the resource in the ground where its value only, its increase in value only depends on whether people are going to want more of it in the future relative to the present. So a critical issue with non-renewable resources is the scarcity of the resource that comes simply from the fact that it's fixed in supply. So because it's fixed in supply, typically there will be a difference between the price of the resource and the cost of extracting it. That difference is called a rent by economists. It measures the scarcity value of the resource. So for instance, in the case of petroleum, the Saudis can pump petroleum at almost no cost at all. It's minimal cost. On the other hand, they can turn around and sell the oil for a fair amount of money, and that's because oil is a relatively scarce resource. And the difference between the revenue they get for selling it and the cost of extracting it is a measure of how scarce it is at the present time and the expectation as well of its future scarcity. Economists typically would argue that that being the case, what the scarcity really means is that we're taking it from future generations. Since the resource will run out at some point or become increasingly less available as we exploit it, then it becomes the case that future generations will have less of it. So if we're getting this extra profit, this rent today because of the scarcity value and depriving future generations of access to this resource, the fair and appropriate thing to do is to take that rent and instead of spending it ourselves, invest it in other things that will be of value to our future generations. That's called the Hartwick Rule. It's discussed in the text. This is considered the optimal policy for any society that's harvesting or extracting non-renewable resources. In the real world, this admonition is rarely followed. Let's move on to pollution. Pollution is an example of externality theory. In externality theory, which we've already covered, the issue is that you have costs, in this case negative externalities, which the producer of that externality does not have to pay for. There's no market in it. Nobody makes you pay for it. So it's not like the things that are privately owned, which if you want to use them, you have to pay for them. In this case, you can use the rivers, you can use the atmosphere, you can use any part of nature that you want and pollute it, and nobody makes you pay for it if it's true externality. To a large extent, the issue of controlling pollution follows the logic of externalities that we looked at before, but there's one issue that should be brought into closer focus, and that is the question of whether it makes more sense to regulate the price of some good, some pollution problem, or to institute a control on the quantity of pollution that can be allowed. So in the case of price, what you're doing is you're taxing the polluter. And this follows what's called the polluter pays principle, the idea that you figure out what the cost of the pollution is to society, and you turn around and you tax the polluter to the extent of that cost. The quantity approach is to set some physical limit on the amount of pollution that polluters can engage in, and then enforce that physical limit. The interesting thing is that if the price-quantity relationship, i.e. the demand curve, is perfectly known, then each approach gives you the same outcome. If you set a higher price through a tax on polluters, that leads to a lower quantity of pollution. If you set a lower quantity of pollution through a control mechanism, that will lead to higher prices. And since what leads from one to the other is the demand curve, and it's the same demand curve, then what you're suggesting from that is that it doesn't matter whether you use a price approach or a quantity approach. However, in the real world, we don't know what the demand relationship is. It's entirely or largely uncertain. In fact, as we'll see subsequently, in many cases, the very concept of a demand curve is questionable. So in the real world, when you don't know the relationship between prices and quantities, what should you do? Should you use a price approach or a quantity approach? And the theory here says it's really a question of which uncertainty you would rather avoid. On the one hand, if you don't know the relationship between prices and quantities, if you set the quantity, the prices become uncertain. So you may say there's a certain amount of pollution we'll allow, and then the price takes off, and you don't know what the price is going to be, and the people who care about prices might be very upset. On the other hand, if you don't know this relationship and you adopt a price approach like a tax, you don't know how much pollution is going to be reduced, and people who care about pollution may be upset. So the choice between price approaches and quantity approaches typically comes down to which uncertainty do you fear the most? Are you more afraid of not knowing how much it's going to cost, or are you more afraid of not knowing how much pollution reduction you're going to have? Finally, let's take up the issue of ecological complexity. Markets, as we'll see in the next lecture, add up individual choices one decision maker at a time. It's a purely adding up process. And if the mechanism works, the whole is simply the sum of its parts. So one example of this might be the market in cars. So a dealership might have a number of cars in its showroom, and people come, and one person buys a car, and maybe another person buys a car, and the total number of cars is the sum of all the cars that people buy, and that's really all there is to it. It's just an adding up process. But ecosystems don't work that way. They are not adding up processes. They are instead the outcomes of highly interdependent cycles and other types of interactions. The carbon cycle, the nitrogen cycle, energy cycles. So nutrients and energy flow through the system, and the different chemical elements within the system interact with each other in such a way that the whole is nowhere near the sum of the parts. In order to achieve the outcome that you want to achieve in the natural environment, you often need to have policies that encompass the interactions between individual activities. They are necessarily systemic or systematic policies. If we want to clean up Puget Sound, for instance, we can't really distinguish my runoff from your runoff, or this particular chemical from that particular change in noise or turbidity or some other factor. All of these different elements combine to create the Puget Sound that we have, and therefore the market approach, which is to put a price on each little piece of it, isn't going to add up to a solution. I'll conclude by saying a word about risk and precaution. One approach to environmental policy, which is the common one used by economists, is to put market values on costs and market values on benefits, and then make comparisons. That's called cost-benefit analysis. Another approach, however, is to think about environmental policy as insurance, where insurance, the goal is to reduce risk, not to maximize benefits, but to reduce risk. A clear risk-based approach is called the precautionary principle. According to the precautionary principle, you need to take uncertainty into account. It's an important aspect of a decision. The more uncertain you are about the outcome of your actions, the more precautionary you should be, the more careful you should be about interventions into the system. Similarly, the more serious the risks, and in particular, the more irreversible the risk, the more precaution you should take about the actions that you engage in. So this is a risk reduction approach, which is somewhat different to the cost-benefit approach typically favored by economists. Precaution is very controversial. There are strong arguments for it, against it, and within it. It's one of the chief areas of debate within environmental policy.